All good? Oh, yeah. All good?
Okay. I think
good host today?
Connor has figured it out.
Kind of? All right. But you're here.
Yeah. Yes.
Oh, you did. That's what we were talking about. We'll get up there. I think it's the gradient for Okay. Okay, everyone. Hi, everyone. I am Connor Larison. I'm a new postdoc with the Transient Group, and it is my pleasure to introduce our colloquium speaker today, Dr. Kishalay, who's coming back not only as a new faculty member from Columbia, but also for the Hubble Fellowship Week as a former Einstein Fellow. He's inimitable and does amazing work on infrared transients. So,
Okay. All right. Is this what good? Okay, perfect. Thank you. Okay. Yes, it's a pleasure to be back here, and mainly because it's just almost a coincidence that I think the Hubble Fellow Symposium is this week, because as of last year and on this date I was a Hubble Fellow, so it's nice to be seeing a lot of familiar faces, not just in the transients group here, but also amongst fellows who were along with me at the time. Okay, good. So I'm going to be talking about explosive transients, especially how infrared surveys are changing our view of the dynamic sky. And it's also nice to be speaking to this audience, because a lot of the work that I'll be talking about was either sort of in one way or another started here, or was enabled by facilities that are operated by the Space Telescope Science Institute. And I'll try to highlight some of those links about how these space facilities have really changed our view of the infrared sky. So something that many of my time domain colleagues would know, something that I really like to stress at the start of my talks, is that the time domain field is not happening in a bubble. I think for our colleagues outside time domain, there can be an impression that, oh, we just cherry pick interesting objects, but it's very much not that. Time domain fits in very neatly into the entire picture of astrophysics, the field of astrophysics. And just to show that, what I'd like to stress is that this is sort of the classic stellar evolution diagram that we teach in courses. It's considered to be common wisdom. If you start, depending on the mass of the stars evolve differently, and they end up either as these more, meek white dwarfs by the end of their lives, or more spectacular explosions that produce neutron stars or black holes. So this is one of the fundamental goals of understanding stellar evolution as a whole, of how stars are formed in the universe. And we think that the end seeds of the end products of this stellar evolution chain end up being the seeds for things that grow to even bigger scales, so that this actually fits into a bigger picture of astrophysics, where the seed compact objects that are formed by stellar evolution likely seed the most massive black holes that we see in the centers of galaxies, and this ends up affecting entire galactic ecosystems over the age of the universe. And the claim I will make, which hopefully I will convince you by the end of this talk, is that despite the beauty and serenity of this picture, none of these processes are as simple arrows as you see. Each of these steps involves an explosive transient in one form or another, and this is one of the things that we are learning. And what that means is that if you want to understand this entire picture going from these gas clouds in the ISM to supermassive black holes in the centers of galaxies, we have to understand the explosive transients. And these time domain surveys, especially of the kind that are operating today, have operated for the past few years, and especially ones that are going to operate. These are really changing our view of the universe and perhaps raising more questions than answers. All right. So a lot of this has been enabled by the advent of time domain surveys. Showing here a collage of different surveys that many of you would be familiar with. The thing I'd like to highlight is that the majority of these surveys in the past decade have been focused in optical light, and that's because big optical detectors have become increasingly affordable, and technology allows us to make these detectors. But doing the same in the infrared has been quite challenging because the atmosphere itself is somewhat opaque in the infrared, it's bright in the infrared, and detectors also tend to be more expensive in the infrared. So we've been trying to push the frontiers of infrared transient astronomy by both from ground-based observations and by essentially taking existing data sets and doing time domain science with them. And that's really going to be the focus of my talk, which is how do you take a data set that was not meant for transient science and sort of reimagine it as a time domain survey. So the highlight of this talk for the most part is going to be this amazing mission that I will try to convince you, called NEOWISE, which has really opened up the infrared sky in ways that I think I at least hadn't anticipated a few years ago. So what do I mean by reimagining a survey in the time domain? Which is that if you take a survey like NEOWISE, WISE was launched in 2009, so more than 15 years ago. I did an all-skies survey for a couple of years where what it did, the basic thing it did was that it had an orbit around the Earth that looked like that. It was sort of always circling around this terminator line between the day and the night side. And you can imagine as the Earth goes around the sun, you end up covering most of this, almost the entire sky over a period of 6 months as it keeps doing these circles around the terminator line. And this is what it did as part of its initial 2-year survey. It created a very deep all-sky map in the mid-infrared bands, going from about 3 microns to 22 microns. But it was subsequently reinitialized at what we today call the NEOWISE mission, which started around 2013, where it was just operating in these 2 wavebands, 3.4 and 4.6 microns, where in the warm mode, it was just operating at these shorter wavelengths, continuing to create maps of the sky. The major driver for this, the reason why it was initiated, was to actually make measurements of solar system objects, which is that as you have these comets and asteroids passing through the solar system, you can get mid-infrared measurements and measure things like albedos and so on. But what we sort of began to realize as we started doing these ground-based surveys a few years ago is that there was this incredible potential in this data set, not just to make measurements of known point sources, but to discover new point sources that may be just lying in the data. And the way that works is this classic method of what we call image subtraction. It's sort of widely used in all time domain surveys in the ground. The idea that if you take, let's say this is an image from NEOWISE, these are real NEOWISE images in 2020, you have a reference image that was taken 10 years before, from 2010, you subtract the two, you see things that pop out. And these are the kinds of things that we are routinely used to finding in ground-based time domain data sets. Similarly, you can see the power of this technique, especially in very crowded fields. So if you look at these 2 galaxies, visually, there's no difference between them. It's almost impossible to tell the difference. But once you start doing image subtraction, you see that there is a point source that sticks out in the center of the galaxy. This, we believe, is a tidal disruption event that occurred in the center of that galaxy. And that's what image subtraction gets you. So what we started doing a few years ago is this idea of just taking the entire archive of NEOWISE data, which is roughly about 1 million images over 15 years, and doing image subtraction on all of them, taking the all-WISE data, which was from 2010, and using the rest of NEOWISE as a time domain survey, start looking for transients in this data set. So this was, of course, a huge operation, and you can see from this number that I showed over here, we initially landed up with this sample of about 5 million sources that change in brightness in one way or another. I can assure you that doesn't mean 5 million transients. What that means is that these include variable stars, AGN, all the things that keep burbling and popping up and down. But it was a huge effort to sort of archive this correctly in a way to be able to use it as a time domain survey. And that led to this, really array of ground-based programs to allow us to follow up these events. So here I'm showing a collage of all the facilities we've used to follow up these events. This goes all the way from optical bands, UV bands, all the way out to radio and X-ray bands, given the diverse nature of things we started finding. And I'll try to go into some of that today. But what I really wanted to highlight, and that's especially important because we are at Space Telescope, which is that these three facilities have been absolutely instrumental in our understanding of this population. Roman is obviously not here yet, but JWST is almost obvious. Like sure, these are infrared transients. You would get infrared data for them. But as I'll show you during the course of this talk, HST has been absolutely instrumental in pushing our understanding of what these transients are, especially because of the very long time baseline that HST brings for sources in nearby galaxies. HST has been operating for almost 30 years now, and that time baseline becomes very critical to, for us to understand the progenitors of transients that I'll talk about today. And of course, towards the end of this talk, I'll allude a bit to what the Roman Space Telescope is poised to bring for us. All right, okay. So here is a group of people that I've had the privilege to work with. A lot of the work that I'll be showing was really done by these people. These are, other postdocs, faculty members, and graduate students who've now become, some of them have now become postdocs, some of them are close to finishing their thesis. And special thanks to Aaron Meissner, who was kind enough to respond to my emails about unwise images, because that's really what enabled a lot of these technical operations that we were interested in. And this is something that I started when I was a Hubble Fellow at MIT, and this has now evolved to sort of what is my group at Columbia University. So this is what that group looks like right now. This is the logo that we made. We have about 3 postdocs and 3 grad students who have sort of just started working on a variety of topics in this. And just in case you are wondering, this is totally not made by ChatGPT. People ask me this question because it's not clear what ChatGPT was thinking here. It looks like a exploding star in a triple system with a black hole in a misaligned orbit. So I'll let you imagine what ChatGPT was thinking in this case, but I think I'm happy with this as a logo. Okay, so in the interest of time, I will actually not get to talk about transients from supermassive black holes. I know there is a lot of interest here in transients from supermassive black holes, but I'm happy to sort of talk about that separately. So I'm going to focus this talk on stellar transients, transients that occur across this life cycle, and honestly really tell you about the most surprising and perhaps impactful discoveries that have come out of this data set by just systematic mining of this 5 million sources. So obviously, if you think of explosive transients, the most obvious one here is this phase over here, where you see there's a supernova that goes off and ends up producing a neutron star or a black hole from a massive star. But the thing I'd really like to highlight is really this idea that this question of what stars form black holes. Turns out that this is a question that we almost, I think, for our students, we teach this almost as common knowledge that sure, every star more massive than 20 solar masses turns into a black hole. Turns out that this picture is probably far from the truth. And if one were to ask what the theoretical understanding was, let's say 20 years ago, this is what that landscape looked like. This is a figure from a very famous review paper from 2002. What this shows is what we think massive stars end their lives as a function of the metallicity of the star. So this is more metal rich, and as a function of mass. So these are more massive stars. The basic idea being that as you go to more and more massive stars, you go from stars that successfully explode and produce a neutron star until you hit a wall somewhere, and then stars do not successfully explode at that point, and they turn into black holes. These are sort of the vanilla, hand-wavy understanding of what stars form neutron stars and what form black holes. Turns out that more recent theoretical simulations are very far from what this picture looks like. If you look at what a recent paper would look like, it shows that what you see here is the mass of the star on the x-axis, and the green indicates a successful explosion that forms a neutron star, and black indicates something that turned into a black hole. The basic idea being that unlike this simple picture where you have very massive stars just simply turning into black holes. It looks more like a picket fence now. Some stars turn into black holes, some stars don't. Some stars successfully explode. It's very messy. And the reason why a lot of this is still very much theoretical speculation is primarily because we can't actually tell when a black hole forms inside an explosion. That's the fundamental limitation. And part of it also being that the most obvious ways in which black holes might form from these massive stars are remarkably difficult to find. So what do I mean by that? What I mean here is that in the traditional picture of how black holes form by essentially a pure implosion of a star, is this idea that you start off with a massive star, it ends its life as a red supergiant, and at the very end of its life, if it's has the right conditions, it actually does not explode, but instead sort of implodes into a black hole. The core collapses back into a black hole and leaves around this heated gas that slowly falls back into the black hole, and eventually produces essentially no explosion at all. What you're talking about here is a massive star that disappears without any signature. So if you had a way to get measurements of millions of massive stars in the galaxy, in nearby galaxies, you would essentially find them as a red supergiant that abruptly disappeared without producing an explosion. That is the canonical expectation. As you can imagine, monitoring individual stars at extragalactic distances is extremely challenging. You have to be able to see those stars. HST is pretty much the only, it's a state of the art. There have been other surveys that have tried to do this from the ground. And perhaps the most remarkable example of this that existed for a while was this star in NGC 6946. It was discovered by a survey being carried out with the Large Binocular Telescope, where what you see here are these are before and after images of what appears to be a supergiant in this galaxy. And between images taken about 10 years apart, you see a star abruptly disappeared. And this was discovered because of a ground-based survey with the Large Binocular Telescope. And this is what its light curve looks like. There have been a series of papers written about this object, where what you see is that between 2000 and 2015, you had this relatively constant source that showed this blip outburst, and then it just abruptly disappeared. There was this one candidate that's been around for a while. I think there have been more recent JWST observations of this, which I think kind of confirm the picture, depending on who you ask. I think that's a bit of a topic to debate. But one of the things that at least I was personally very interested in is this idea that if you look at these optical light curves, so these colored points are all optical light curves, there is also a clear infrared signature where you see that these are Spitzer light curves of the same object. You see there is this slow brightening and then very slow fading away. In fact, even today, it's actually a mid-infrared source that JWST can detect. So this comes from a classic prediction that was made around the time when this survey was happening, which is that these failed supernovae, because they have these sort of extended envelopes and eject very low amounts of mass with low energies, these are the ideal sites of dust formation. So it's not entirely surprising that you see an infrared glow after these. And this is great because it means that even if you couldn't monitor individual stars at extragalactic distances with the kind of resolution, you could actually use the infrared brightening and fading as a way to find potential candidates of interest. And that's where the WISE search comes in. Okay, so what we've started to do right after we started this project was this idea of looking for these luminous infrared outbursts in nearby galaxies. One of the most remarkable ones that actually came across was, so this is sort of a collage of different things that we find. I was telling you how image subtraction allows us to find things on top of galaxies. And you can see here that these two images of the same galaxy, you subtract the two, there is a source that pops out. This is what the power that image subtraction brings you. And it turns out that we didn't have to look very far away to find perhaps one of the most interesting candidates we found. Turns out that we found it in this galaxy. Hopefully everybody knows what this galaxy is. This is M31, our nearest Milky Way-like neighbor. So we had a Keck program to go after luminous infrared outbursts in these nearby galaxies. And here is a cutout WISE. These are WISE images of a section of M31. You see there are these three stars right next to each other. 3 stars, and one of these stars, the top one over here, it showed an infrared brightening around 2014 that was flagged by our pipeline as, oh, something changed in brightness, had an infrared outburst. And one of the cool things of being able to study things in nearby galaxies is that there is huge amount of archival imaging. This is actually an archival 2-mass image, so like a tiny telescope. You can see there is you can see the source even in 2-mass from 1995. So like, sure, let's go and see why it will.
Can we cannot see the screen on Zoom. Can somebody take a quick look, please? We've missed the last couple of slides.
Okay. No. What do you see right now? Okay.
We see the video of the auditorium, but we do not see the screen share.
Oh.
Just tell them we've contacted.
Okay, we've contacted the team here, and hopefully they will figure it out. Okay. Yeah. Okay. Right. So one of the really neat things. Oh, thank you. One of the really neat things of looking at things in nearby galaxies is that there is this beautiful archival imaging. This is a 2-mass image, so it's fairly shallow. I was like, sure, let's go and take a spectrum of this object to see why it decided to produce this amount of dust. So I was actually in Waimea in Hawaii, getting at Keck, trying to get these observations. I was like, sure, here's my finder chart. I'll go point Keck at it. Boom. This is the same field. You see 1, 2, 3, 1, 2, nothing. So I was like, wait, it was like 3 in the morning. I was like, wait a second. Like, am I going crazy? So my reaction quite literally, I mean, if you ask the operator, there was like, basically this. I was like, how does a star that was detected in 2-mass 20 years ago, how does that disappear in an image taken with the largest ground-based telescope? This does not happen. I've done hundreds of observing nights, and this does not happen. All right, so this is really where the story started, in that I didn't actually end up getting a spectrum of this object, but apparently the discovery was already made. This is where some of the legacy archive of things like HST become very useful, because again, HST has mapped this entire galaxy in great detail over multiple epochs. So what you see here is actually that same star observed with HST. So these are 3 different filters observed from around 2012. And you see at the position of this very bright source in 2-mass, you actually see there is a very bright source in HST. Not an entire surprise. And then you ask what did it do after that? We can accumulate all the WISE data, all the data from ground-based surveys, and this is what that light curve looks like. This is the WISE data. This is in W1 and W2. You see it had a blip, faint infrared brightening, and then disappeared. And perhaps what is more surprising is this, boom, just disappeared in the optical. So much so that, again, we didn't have to get any follow-up. We just went to the HST archive and found images of it after it disappeared. You see, this source, that booming infrared source, nothing, nothing, nothing. And if I know anything, if something is not detected in HST, it's not there. That was one of the key ways we interpreted this source, is that if you don't see it in HST, there's not much hope from the ground anyway. So what we think this is a supergiant star. I'll come to that in a bit, that disappeared essentially in our very nearby galaxy. And this is what I like to just take a pause. We have this entire community of astronomers looking for transients at redshift 5. A star disappeared in M31. Nobody noticed. Like the number of sleepless nights I've had because of this fact is absolutely, it's mind-boggling to me. Right. So back to the basics. What can we tell about the properties of this star? One of the cool things is that it has this beautiful SED combining HST and Spitzer. We can combine all of this measurements to create a SED and fit a model to it. It looks like a supergiant with some sort of an infrared excess around it, as we can tell from the Spitzer bands. And you can place this star on a HR diagram with some tracks on it. Turns out that it falls quite neatly on a relatively massive track. The details depend a bit on the stellar evolution model you adopt. But the idea is that it appears to be a bit bluer than what you would think a red supergiant is. Red supergiants are usually on this track, this this Hayashi track that you see over here. This one turns out to be a bit bluer. So we think it's a yellow supergiant with an extended dust shell around it. That's what causes it to be sort of somewhat bluer spectrum and has a dust shell around it. So if you're thinking of what this star might look like, this is basically what it is. It's a star that has lost some of its hydrogen envelope for some reason, and then it has an extended dust shell around it. But what is really remarkable is that if you see the transition of the object 10 years apart, it looks something like this. So it went from being this very luminous star that was detected at optical wavelengths to this star that had completely, so this is, by the way, 5 orders of magnitude. So this is huge. Stars don't usually disappear like that. And you see that there is this faint infrared glow that sticks around, and you can fit a SED model to it. The main takeaways is that this star has faded to less than 10% of its luminosity. There is no evidence, because it's such a nearby object, for any type of transient that it showed, no supernova at this position, and it became slowly enshrouded by dust. So what we think is really this has opened our eyes to what appears to be almost a textbook stellar implosion. The idea that you have a star that was around happily chugging along, and then suddenly it disappeared. We think the properties are very well explained by the formation of a black hole in the center of the star. And as it did that, the outer stellar envelope begins to fall in, and then many models of these so-called failed supernovae show this idea that the envelope isn't able to accrete directly into the black hole because it has too much angular momentum, so that it sort of very slowly accretes back into the black hole, and it fades away slowly. And we can actually confirm that because we have a light curve of it. Here is the light curve of this object, luminosity as a function of time. It was fairly flat initially, and then it just begins to follow a perfect power law. It's t to the minus 5/3. And again, we can tell this because we have this exquisite archival coverage from a number of different surveys. And all of these properties are fairly well explained by a very low energy shock that happened just as the black hole was forming, and then the star disappeared. All right, so here again, JWST has been instrumental. We put in a JWST DDT to get mid-infrared observations of this source. So thank you for approving this DDT. What you see here, these are MIDI images of the source because it's a very bright mid-infrared source. This is the source in the center. We were actually worried about saturation for a bit, but I think we ruled it out. But this is a MIDI multicolor image. And the main thing that JWST allows us to confirm is this. There's this common thing that maybe the optical disappeared because there is dust formation and all the luminosity is emerging at long wavelengths, infrared wavelengths, because of some exotic dust formation episodes. JWST basically rules that out. So here you see that this is the progenitor star, which was like 10 to the 5 solar luminosities. And you see that at no wavelength out to 30 microns is this star brighter than its progenitor. It's basically now about 5% of the luminosity of the progenitor. This JWST rules that entire interpretation out. So the only thing to say is that this is some star that abruptly disappeared and truly disappeared in bolometric luminosity to about 5% of its progenitor, and it's continuing to fade now, as JWST confirms. All right. So let's see. Any questions about this? Yes. Oh, yes.
Maybe this
yes.
numbers don't work out at all. But
yes.
Is it possible that there's a dust formation episode that's gathered up all the bolometric luminosity?
Yes.
It's actually absorbing it, and
yes.
it's going to come up later. Can you rule that out?
Right. So I think there's the light travel, like the travel time argument over there, which is that this is a star. We can measure the size of the dust shell based on the SED, and I think it's difficult to hide that luminosity. Like the idea is that if the star is still alive inside, that luminosity has to go somewhere if it exists. Yes.
Would you expect to be able to detect these in any really deep X-ray or radio bands after the disappearance?
Right. So that's something that has been suggested. We do have Chandra observations of this source. Turns out that even though it's very nearby, you can see in this picture here that you basically have a black hole that's surrounded by like half a solar mass of gas. It's a huge amount of enshrouding, and typically you would expect these to emerge, if at all, like in decades. So yes. Yes. So maybe by the time I retire, yes. Right. Okay, good. So let me move on to the next part of this talk, which is that, and I know, there's a lot of topics, individual topics that I know might be of interest to this group, but I kind of cherry-picked for the ones that I think might be of interest specifically to the folks here, which is this, sort of going a step back, which is this idea of understanding massive stellar death, because it's very closely related to, this entire topic of, black hole formation and neutron stars and so on. So one of the things that's become very clear from time domain surveys is this idea that massive stars by no means have calm deaths. They turn out to be very violent at the end of their lives. They eject mass. They do all kinds of exotic stuff at the end of their lives. And then they explode, producing supernovae that have somewhat interesting observational signatures that we can routinely detect in surveys. So the question that we started to ask with some of this, and again, this was motivated by a lot of the work done over here by the transients group here, which is this idea of what can we tell about pre-supernova mass loss from massive stars by using these infrared surveys. So going back to that picture, the general idea is that we think massive stars eject tons of mass at the end of their lives. This is obviously a cartoon picture. It shows a hydrogen, a massive star that is surrounded by some dense CSM. The typical way in which you infer the presence of dense CSM around exploding stars is that when they do go supernova, the supernova ejecta interacts with this outer CSM shell, and you start seeing all these signatures that the ejecta is being slowed down by a dense CSM shell. So this shows a schematic of that. And the classical example of that are what is called the interacting supernovae that show these remarkable spectroscopic lines. And I've lost track, but there are many varieties of these now, type 2N, 1BN, 1CN, 1DN, 1EN. I want to ask people here, one of these is not a real supernova type yet. Which one of these is it? Who knows this? What's that? Yes, 1DN. So type 1DN is not a supernova type that has been observed yet, but we think it should exist based on our understanding of stellar evolution. Okay, yes. So this is commonly what we use to infer the presence of pre-supernova mass loss. These are type interacting supernovae. But what I really want to focus on is that what you see in this diagram over here is that in the presence of these shocks, these turn out to be quite good sites for dust formation, and they produce dust. They also heat dust by, they can heat dust because of the shock radiation itself. So, of course, this only happens if you see the supernova, observe the supernova by the time it's crashing into the CSM shell. Imagine if you had a shell that was not so far in, so close to the supernova, but was very far out. Like, this is mass that was ejected thousands of years before the star actually collapsed, in which case, just because the ejecta is traveling at 10,000 kilometers per second, this would take of the order of 100 years, 1,000 days to even reach this material, because the supernova ejecta takes time to expand. There, what we've seen, and a lot of the work has been again pioneered here, is this idea that even if you can't follow up the supernova at very late times because they get very faint in the optical, you can actually use the dust emission, which emerges in the infrared, as a way to infer the presence of these very distant CSM shells that massive stars might harbor at the time they collapse. So this is a plot from Tamás Zalai's paper, which shows some manifestations of these in their infrared light curves. These are a collage of infrared light curves of core collapse supernovae of various types. This is absolute magnitude as a function of time from explosion. There is this very neat class of explosions that show this very luminous late time infrared emission, which we think comes from dust being heated by this shock that is caused by CSM that is very far away from the star. And Ori has done some of the initial work using Spitzer to find these events. And of course, there's a huge amount of literature, again, from the group here on using JWST to go back and look at very nearby supernovae to look for this dust emission that might be produced by shock interaction. But what we've actually turns out that JWST observations are obviously great. They're somewhat expensive to get for individual objects. But NEOWISE, being an all-sky survey, you can almost sort of blindly look for these luminous dust formation episodes, even without knowing where the supernova is. That's one of the advantages of having an all-sky survey. So what we started to realize was that you could use this luminous late-time emission alone to discover supernovae for things that are very strongly interacting with CSM shells that are very far away. And this is work that was led by my student, Charlotte Myers, who's an MIT undergrad. What you see here is at 3 WISE images again. You see there is this thing that pops up next to this nearby galaxy. It's about 180 megaparsecs away. And this was again flagged by our pipeline as a luminous infrared transient in a nearby galaxy. It's usually not easy to tell what things like these are until you start comparing them to other objects. And this is what that looks like in that same phase space plot, absolute magnitude as a function of time. If you plot this object on top of all of the other objects that Spitzer has observed, you see that it ends up being one of the most luminous infrared transients ever known. It's like absolute magnitude of -22. Yet, this was not even identified by any optical survey from the ground because it was just a very meek supernova. The supernova itself was very faint. It was maybe 20.5 magnitude in the optical. That's barely what ground-based surveys get to. But it was very obvious in WISE because of how luminous it was in the infrared. So we went back, got a spectrum of this source. Turns out that you can confirm this is an interacting supernova. This is the black lines here are this object from WISE. You can compare it to other interacting supernovae that all show these optical spectroscopic lines. So discovery in the infrared, you go back in the optical and you confirm that these are indeed showing very strong signs of CSM interaction, even though they were not discovered optically. And when you go back and look at the archival data, it turns out that you see there is a very faint supernova that was detected nominally detected in ground-based surveys, but never flagged for follow-up, despite it was very nearby. But you see that in WISE, it really shines as a very bright infrared supernova. Okay, so one thing that I get asked commonly is that were we just lucky in that maybe objects like these are 1 in 10,000 or something, so there are only few of these going on. So we can quantify that again because we have all sky coverage from WISE. Here I'm showing actually a collage of optical light curves of supernovae that are not actually that noteworthy apart from just being core collapse supernovae. You see that this is magnitude from peak as a function of time. Most of them have these just drop-offs at late time. Some of them have these very faint bumps at late times, which may or may not be discovered depending on how sensitive your survey is. And you wouldn't actually notice these supernovae by themselves. They're kind of vanilla core collapse supernovae until you add in the WISE data, and then you see they all show these luminous mid-infrared brightenings at late times. So we can quantify this very well because WISE is such a systematic survey. It's about a few % of core collapse supernovae actually show this, which is that if you look at their infrared emission 1,000 days after explosion, they all show signs of interaction with, very strong interaction with distant CSM shells that are not at all obvious in the early time data. So, and this is, I think these will be quite common in the high latitude time domain survey for Roman because it's an H band, it's very sensitive, and just a back of the envelope estimate would tell you that there'll be a few hundred of these just floating around in the high latitude time domain survey fields. These are not high redshift objects, but they almost look like high redshift objects because they have such a red spectrum from the dust. So this will be an interesting exercise for high redshift discovery. But in preparation for what we are poised to learn from Roman, what we started doing is, again, ground-based follow-up for some of these events. Here, again, you can go back and confirm that many of these events are indeed interacting with dense CSM. This is a spectrum that we got from Magellan of one of these events. And we just have approved a cycle 33 program to get UV observations of all of these. The last set of luminous supernovae detected in NEOWISE from infrared bands. So the idea here is that what we are probably seeing is that we have some sort of a dust shell around a star. It's being heated by the UV shock interaction inside, and this is what the dust is radiating. What we hope to see and hope to quantify is this idea that can we see the UV emission directly from the HST observations by getting UV imaging of these things around the time that the infrared emission is on. So these observations are hopefully going to happen over the next year or so. Okay. Okay. Right. Before I move on, any questions about that? Yes.
This last cartoon is interesting because it moves out from the spherical symmetry.
Yeah. Yes.
7A luminous blue variables.
Yes.
All this stuff is bipolar, it's not symmetric. How this changes your calculation about the balance of infrared radiation absorbed, emitted? Because you can see to the pole, you can see to the equator. How much variability this introduces?
I think asymmetry is what we absolutely need to explain these events, partly because in most of these events, you do see an optical supernova with no signs of any large dust extinction. But at the same time, at late times, you see there is this dust that is there. So the question is, what if it was completely covered by dust in all directions? It would be, you would see signs of it, like some sort of attenuation in the optical data of the supernova itself, which you don't see in most of these cases. So I think one of the things we are hoping to measure with this is really that if you take the UV luminosity of the event and the infrared luminosity separately, does that allow you to estimate essentially the covering fraction? Because both of those, the dust emission is being heated by the UV luminosity of the shock. Likely, that's the likely interpretation of this. Okay, good. So I'm going to switch to sort of the last stellar part of my talk, which is that I really go back, sort of shift this from this chain to this chain over here, go to low mass stars. And when I start talking about low mass stars, a lot of people are like, oh, low mass stars are boring, they don't explode. But what I want to convince you is that low mass stars are by no means boring, even in terms of the transients they produce. And we're starting to see, we sort of almost knew of this for many years, but we're starting to see evidence of this directly from time domain surveys. And in fact, you don't have to look very far to find evidence of explosive events in low mass stars if you just go and look at the remnants of low mass stars. So these are, again, remnants of low mass stars. These are what we call planetary nebulae. And as you said over here, the remnants of low mass stars actually have these remarkable shapes. Some of them have these dumbbells, some of them have these outflows, quite remarkable shapes. And it's not always clear why would, let's say, a star that is living by itself end its life with these remarkable shapes. What is producing the geometry that produces this type of shape that we see very commonly? I'd say almost every, depending on who you ask, almost every planetary nebula actually looks like this. Like no planetary nebula actually looks circular. So one of the most popular ways in which you can get this is this idea that you can because half of stars have companions around them. Probably every star has a planet around it. So if you imagine a star ending its life as an AGB star and turning into a planetary nebula, almost inevitably planets like these would shape the outflow as the AGB star is forming and ejecting its outer layers. And this has been one of the most popular ideas of explaining why planetary nebulae can get shapes that look like that. So the picture here is that you have stars that are essentially starting to interact with their planetary companions. And this is something that has been very widely discussed historically, because this is the idea of planetary engulfment. You have a planet being engulfed by a star. If you look what one of those theoretical simulations look like, this is what happens when you have a planet merge into a star. What you see here is this remarkable outflows and essentially a transient explosive event that you might expect. And in case you believe that this was a merger of a star with a planet, I've just fooled you, because this is actually two stars merging. This is what a star merging with a planet looks like. The main thing I want to drive is that stars merging with planets are much meeker events, much sort of scaled down versions of stars merging with stars, simply because the planet is at least 1,000 times less massive than a star. So the effect that the planet produces on the star essentially is a scaled down version of what we see in events where we think two stars have merged together. And this is great because we have some idea of what stars merging with stars look like. We today call them luminous red novae, as many of you would have heard of. The idea that these are events that we see in other galaxies. This is one that occurred in M31. You see this brief optical outburst that occurs when two stars merge, and then you have this very long-lived infrared glow that is caused by the dust that is formed in these events. So you can almost see that these are very nicely pure infrared events in some ways, in that the optical is very short-lived, 60 days roughly, 2 months, 3 months, but the infrared can live on for years, sometimes decades, depending on the type of star you're looking at. So this is great. This is, again, a problem that is very well posed for infrared discovery. So we started looking for examples of these in nearby galaxies, and we were kind enough to say that we will also look in our own galaxy as well, just in case one of these occurred sometime in the last decade. And this is where the story of this particular star begins. This is this star that you barely see. This is an archival image from UCURT, which from the UCURT Galactic Plane Survey. This is not a star you would notice for any reason. It's just a faint red star in the galactic plane. And the only reason we started noticing this was because in May of 2020, it did something like this. This is a ZTF light curve of this star. You see it was basically not detected forever before this outburst, and then it boop, went into outburst and slowly faded away in the optical over the next 200, 300 days or so. And again, this is not something you would notice. There are hundreds of things like this that go pop, pop, pop in the galactic plane. There's too many of these things going around. The main distinguishing feature that really alerted us to this object was that if you add in the WISE light curve, you see that it had this slow precursor going up to the time of the outburst, and then a very long-lived infrared afterglow after that. This does not usually occur with your vanilla run-of-the-mill galactic plane outburst. It almost starts smelling like a red nova, if you will, because you see the same feature where you see an optical outburst accompanied by a very long-lived infrared afterglow. It's not the same afterglow that you're thinking of gamma ray burst, but it's a glow that lasts. So what we think, we had spectroscopy of this event, fortunately around the time of the outburst, and based on all the arguments we could put together, the only story that fit was this idea that you have a planet that was being engulfed by a star, essentially 1,000 times lower luminosity analog of a stellar merger, but in the galactic plane. This is a nice animation that was created by our colleagues at IPAC, this idea that if you have a planet, we think this was an analog of what we call today as hot Jupiters, these very close-in planets around stars. The idea that as some of these stars die, they can the planet would get too close to the surface of the star and essentially start getting ripped apart until it falls into the falls into the star, and then you get this luminous brightening that we see in the optical data, and you see this glow that in the infrared because of this dust that's ejected. So here again, JWST has been quite instrumental. We were fortunate in that we had a GTO program that was happening around the time we found this object. This is a JWST spectrum of the remnant of the transient. This is MIRI LRS and near-spec data. The two key things is that we see clear evidence for these beautiful emission lines in the near-spec spectrum, which signals the presence of an accretion disk around the star itself. And the animation that was created by the JWST team was this nice thing where you have a planet that was slowly spiraled into the star, but it left behind this almost fallback accretion disk, if you will, which produces these signatures that we see. These signatures are actually quite common in protoplanetary disks. You see evidence of an accretion disk around the remnant star. Okay, any questions about that before I move on? Okay, good. Okay, good. So those are the main science topics I wanted to talk about. So the rest is going to be sort of stuff we're doing right now. This is sort of stuff we've done over the last few years. What I did want to highlight is that I haven't covered this entire phase space at all, and there's too much to cover, and I'm happy to talk to individual people interested, but we have all the way, across this entire chain, we have things going on. We have eruptive young stars in WISE, we have stellar mergers in WISE, we have debris disks around white dwarfs, we have X-ray binaries and novae, we have type 1a supernovae in WISE, we have TDEs in WISE, we have AGN in WISE, and we even have like redshift 6 quasars showing variability in WISE. It's really the amount of data that's time domain data that's been provided by this mission is quite unique, and is producing all kinds of discoveries in this chain, and I'm happy to talk about others who are interested in any of these topics. Okay, so what's next? So let me just leave you with some of the projects that we are personally excited about in the next few years. which is that the main thing being that we've only covered the brightest transients in NEOWISE. I told you it's like 5 million sources. We probably just followed up 100 of those. Part of the reason is that when you find things in the infrared, it's remarkably difficult to get follow-up from the ground because these are infrared objects. Some of them have basically no near-infrared counterparts at all. So it takes a lot of time to do spectroscopy of these things. And unfortunately, as you know, NEOWISE ended last year. One of my students who was working on this project created this animation when NEOWISE crashed into the ocean. I guess crashed is not the right word, but it was decommissioned into the ocean. But the main thing I want to highlight is that what NEOWISE leaves behind is a legacy of very long-lived infrared transients. So examples like these, where this is a WISE light curve of a star that basically was flat for 15 years and boom, it went into outburst right around the time the mission was ending. You can see what this movie looks like. You can see the boom, 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 boom. Boom, yes, that's the transient, okay? So what I'm trying to highlight is that these NEOWISE leaves behind this legacy of very long-lived infrared transients, and you can see even in the last epoch of NEOWISE, the transient was active. It's still on in the sky. You just have no way to observe it apart from getting some way of infrared observations from mid-infrared observations from space. And this is where I think probably one of the things I'm very excited about right now is that SPHEREx is here. Right when NEOWISE ended, SPHEREx started operating earlier this year. SPHEREx essentially provides spectroscopic capability at a sensitivity similar to WISE at a very low resolution. So here I'm showing from the SPHEREx team the sensitivity of SPHEREx as a function of wavelength. It's a low resolution infrared spectrograph going from 0.7 to 5 microns. The sensitivity is almost basically the same as what WISE was doing in its 15-year survey. So for those of you who are not familiar, SPHEREx is this new mission that actually gets a spectrum, infrared spectrum of the full sky. These are actual SPHEREx images. The main technology here is what is called a linear variable filter. The idea that each of these stars, as they fall in different parts of the detector plane, they get sampled at a different wavelength. So you get essentially full, color coverage of the same object across 100 spectral channels. And what we've started doing is that for this sample of transients where we know because of NEOWISE where they are, we can start creating spectra of these objects at low resolution in the infrared. And just to convince you that that is possible, these are examples of what we think on the top. This is an actual SPHEREx spectrum of a likely stellar merger that happened in a nearby galaxy. See, there is this broad water absorption features. There's some ice absorption possibly somewhere here, but it looks like that. This is actually a galactic nova. You see continuum and boom, emission line, emission line. These are actually all bracket and Paschen emission lines that you see in the SPHEREx data. So this is, really helps us with the spectroscopy bottleneck that we've had for these low infrared transients. So of course, it goes without saying that LSST is coming. It's almost here. What LSST will do is, very nice survey of the full sky. The part that I'm personally excited about is again the galactic plane because it will be a game changer when it comes to slow galactic transients because of the cadence. LSST has a fairly modest cadence, so like 2 weeks or so in the same filter. And what you can do is you can ask, what does a planetary engulfment event like the one we found look like in LSST data? And you can simulate that with a real LSST cadence, and this is what it looks like. You see the main features. It's a very slow, long-lived red outburst that we can find in streams like LSST despite the issues with the cadence. So what I'm really hoping is that I see a lot of my exoplanet colleagues show this plot, which shows the number of planets discovered as a function of year. So as you can see, over the last few years, the number of exoplanets known has really skyrocketed because of all of these transit surveys and so on. What I'm hoping is that starting this year, we will start to see this number down as exoplanets get destroyed by, engulfment. Yeah, sorry, my exoplanet colleagues. Yes. Okay, right. And of course, I mentioned Roman at the start. What Roman brings, especially in the landscape of galactic transients, is this exquisite sensitivity over a very wide area coverage. So I'm showing this plot from the Roman Galactic Plane Survey Committee report, which I had the pleasure of serving on. This shows the final decision, or let's say almost final decision of what the Galactic Plane Survey covered. I see Eddie. Hi, Eddie. Yes, yes, Eddie was also on the committee, yes, of what the galactic plane coverage is going to look like. It's a very wide patch of the galactic plane, but the main thing to notice here is that the point source sensitivity of this survey over this 1,000 square degree region is exquisite. It's unparalleled when it comes to other surveys and at the spatial resolution, which is absolutely important for galactic plane studies. And what this really brings is that unlike previous cases where we've had to, like, we find a transient from a ground-based survey, you have to go and get adaptive optics follow-up of these things with, you know, high resolution ground-based imaging. Roman basically gives you that for free for thousands of things that are to be discovered in the galactic plane when it comes to outbursts. You just get this for free for very large numbers of objects. So the other thing that I like to highlight with Roman is that one of the things that the committee decided was to do time domain surveys of the galactic plane in certain sections. Here I'm showing one of the regions right around the galactic center. It sort of covers this very interesting niche in cadences, which, you know, is of the order of, you know, cadences of the order of the minutes to hours to weeks, to be a completely new space, I think, for infrared surveys of the galactic plane, and somewhat uncharted in my opinion, because from the ground it's very difficult to do this, because, you know, just getting big infrared detectors from the ground is very difficult. But Roman is going to do this starting probably in 2 years from now. And one of the things that me and my group are trying is that we actually have, I'm showing you, we're trying to do some of this from the ground already. So this image is actually an image from the Roman H4RG detectors staring at the galactic center. So Sagittarius star is somewhere over here. This is the same Roman H4RG detector mounted on a telescope. If you're curious to know how I got this image, come to Astro Coffee tomorrow. I'll tell you the story behind this. All right, so that's it. That's my talk. I'm going to leave you with some nice images of these WISE stars exploding in WISE, but perhaps the most interesting one, which is at least gives me goosebumps, is this image of this star that, you know, the black hole. You see the star, gone. Yeah, imagine a black hole just formed in that process. All right, thank you. Yes.
Before we,
sorry, yes. Oh,
sorry,
yes.
Before we ask questions,
Yes.
we have 2 more spots for dinner at our house. If anyone's interested, I'll talk to Ori quickly. And yeah, please feel free to ask questions.
Yes.
I was intrigued by your examples in which you think that dust was newly formed as part of the outburst. And my question is, what are the prospects for the kind of spectroscopy these objects that would tell you something about chemical composition or size distribution?
Right, yes. So I think in terms of chemical composition, I think the first order thing one can ask is like silicates or graphite or something. I think so in terms of large scale studies, it's difficult. I think, you know, these programs that Ori and other people here have led of these sort of survey programs of large numbers of nearby objects, I think that is one of the most promising ways to measure dust compositions in these explosive transients. I suppose, I mean, SPHEREx is not particularly good for that because it doesn't cover the interesting wavelength range around that silicate, that 8 to 10, 12 micron region. But I think large survey programs are probably the way to go to measure dust compositions.
I think that these transients are of special interest because you can see the process.
Yeah.
We know very little about how dust gets to where it is in the interstellar medium.
Yes.
And here you'd be catching it in the act.
Right, yes, yes, absolutely, yes. So I think, yeah, JWST is already doing a lot of that, yes. Yes, go ahead, sir. Yes.
So thanks for this episode. So overwhelmingly broad tour to transient. I'm curious about this thing you said about SPHEREx though. So yeah, SPHEREx, this is very different in that every spaxel was a different time. Right?
Yes, yes.
Is that helpful or harmful to you?
So because the NEOWISE transients are remarkably slow by design, because NEOWISE had a 6-month cadence, so I've looked at SPHEREx data. Usually they'll be like all the observations taken a few hours apart. We're okay with that. These things are not changing on hours timescales. But sure, there could be other cases where it's not true. Yes. Yes.
Yeah, I wonder what fraction of exoplanet debris gets ejected and could be a source of interstellar dust.
Exoplanet debris.
From your...
Okay, I see. Right, so I think from well, I mean, obviously some of this is theoretical understanding, but from what I understand from my colleagues who simulate these things, when you have a planetary engulfment event, most of the ejecta is actually the stellar material that's ejected. The planet kind of just gets disintegrated inside the star itself. So most of the ejecta is still just the star material. We've had hopes of trying to measure how, one of the common things that's been floated around is that maybe stars get polluted by planetary ingestion, and maybe someday if we had a nearby object to measure that, that could be done. But yes, as far as the ejected material is concerned, it's likely mostly stellar material. Yes?
Maybe on that point, like maybe around smaller stars and very extremely large planets, maybe
yes.
that you would, but on another question.
Yes.
For your like CSM interacting supernovae,
yes.
how do you disentangle emission from dust forming the supernova itself in like a cold dense shell, and then like CSM interaction later on?
Right, you mean the situation between new dust forming as opposed to a pre-existing dust shell that's being heated by, right. So I think some of these arguments, the limitation here is that WISE gives you two-band photometry, and that's all what we see from the dust itself. But the majority of our arguments have been just, if you take the dust continuum from WISE and you fit a radius to that thing, then you can get a lower limit on the radius of the thing. And usually in all of these cases, because these are so luminous, I think by selection, the radii turn out to be so large that there's no way the ejecta would have reached those radii by the time, because we know when these supernovae exploded, because we have the optical counterpart. And in most cases, the dust is too far out for the ejecta to have reached that radius. Oh, is that a question there? Sorry, was there a question online? Sorry, please. No? Okay. Okay.
Well, let's
okay.
Let's give Kishalay a round of applause. Can't really take any hosting credit. I don't get all the but I will close it out and make it look like I did all the That's my MO anyway. Thank you all. No SS today. We couldn't find a host, although there is beer in the fridge, so bring something and have it. Otherwise, we're going to our house at 6 o'clock. Why not? There's plenty of room for many people. And so we can see there. Thank you again.